what different kinds of values do different materials have? Well, for example, conductors, we would expect to be very good or be able to have current flow through them very easily. We would expect them to have very low resistivities. They do not make good resistors, they make good conductors. So, for example, copper has a resistivity of 1.72 times 10 to the minus 8 ohm meters. So that's copper. Another good conductor is aluminum. Aluminum has a resistivity of 2.82 times 10 to the minus 8 ohm meters. So that's aluminum. So notice very small numbers for copper and aluminum. They are good conductors. Now, what would be an insulator? Well, what's the material that goes over wires when you've got wires in the wall or something? Well, rubber or plastic, something like that. Well, rubber, hard rubber. Now, depending on how the rubber is vulcanized, depending on the different kind of rubber, it will have different values for the resistivity. But they can range from, say, 10 to the 13th to 10 to the 16th power. Extremely, extremely high values of resistivity. Now notice, what's the difference between these things and these things? Well, they are on the order of 10 to the 21 to 10 to the 24 difference. That is an extremely large variation in values. So, copper and aluminum, much, much better conductors. Rubber, much, much better insulator. So, let's stick some numbers in here. Let's imagine that we have a wire. So, a very, very long copper wire. Let's imagine that the diameter of this wire is maybe 1 millimeter. So we've got a thin 1 millimeter copper wire. And let's imagine we've got 100 meters of this wire. So a very, very long spool of wire, say. What kind of resistance are we talking about? Well, R equals rho L over A. So for copper, resistivity is 1.72 times 10 to the minus 8 ohm meters. The length, 100 meters, divided by the area. Now the area, that'll be the cross-sectional area of this wire, which is a circle. Area of a circle is pi r squared. So pi times r, well, if the diameter is 1 millimeter, the radius will be half a millimeter, or 0.0005. So that'll be half a millimeter. Meters squared. We divide that out, and what do we get? We get 2.12 ohms. So, for a very, very long piece of wire, we still only get a resistance of a couple of ohms. So typically, any time that we have a circuit with a resistor of 10 ohms or 100 ohms or 1,000 ohms or something like that, the resistance of that resistor is going to be much, much larger than the resistance of the wires that we'll be using. All right, so one more point. I want to go back to the AC circuits just for a minute, because we'll be talking a lot more about AC circuits later on, but I want to give you just a little bit of an introduction. So remember, I said that for an AC voltage source, we have a voltage that's oscillating back and forth. And we will assume that our voltage source actually oscillates sinusoidally. So we'll write this as V is equal to V naught sine 2 pi f times t. And those are all the argument of the sine function. So if you'll remember, this is something maybe familiar back when we were looking at simple harmonic motion back from 1111, where f is the ordinary frequency of the voltage, which tells us the number of cycles per second that our voltage is oscillating. So if the frequency was, say, 10 hertz, that means this is oscillating back and forth 10 times per second. the voltage is then oscillating with time, and the amplitude is V naught. So what this means is that our voltage, if we were to graph this as a function of time, it's going up to a maximum of V naught and then down to a minimum of negative V naught, and it's oscillating up and down with F cycles every second. Okay? Now, because this quantity 2 pi F is often going to be together, 2 pi times F, we'll write that as a single quantity and write this as as V naught sine omega t, where omega is equal to 2 pi F. And omega, if you'll remember back from simple harmonic motion, this is what we call the angular frequency. And it is basically telling us the number of radians per second. If we take one oscillation of our voltage, one sine wave, we break this down into 2 pi radians, kind of like breaking our circle into 2 pi radians of angle, breaking our cycle into 2 pi radians of phase. Then every cycle corresponds to 2 pi radians. We have then 2 pi F radians per second. So omega is telling us our angular frequency. How many total radians per second is our voltage oscillating through? Okay, so let's keep in mind, we're going to write V then as V naught sine omega t. So, to sketch this again as the function of t, V is going to look something like this. All right, there we go. Now, what's the average value of our voltage? We might write this as V sub average, or V with a bar over it, or V in brackets. They all mean the average value. So if we look at this voltage over time, what's its average value going to be? Well, notice it's just as much positive as it is negative, and so the average value is going to be what? It's going to be 0. Well, that's not a particularly useful quantity. Just to say the average is 0, it doesn't tell us anything about what the amplitude is, doesn't tell us anything about what the frequency is. It's always just going to be 0. So that's not really a very useful quantity. How could we get some kind of average value of this that would be useful? Well, the problem with this being 0 is because we have just as much positive as negative voltage. If we could make it the quantity that we want to average, if we could make it always positive, then the average wouldn't be 0. So why don't we look at the voltage squared? So if this is the voltage, and it looks like this, what is the voltage squared? Well, when the voltage is 0, the voltage squared will be 0. So it's going to be 0 here, 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 here. When the voltage is positive, the voltage squared will be positive. And when the voltage is negative, the voltage squared will also be positive. So what it will look like is something like this. Going from 0 to V naught squared. Now, what's the average of that? Well, from symmetry, we could see the average of that is right in the middle. The average of V squared will be 1/2 V naught squared. Okay, well that's great. That gives us an average value that's useful. It depends on the amplitude of the voltage. But it's a squared quantity, so let's take the square root of that. And what do we get? Well, the square root of 1/2 is 1 over root 2. Square root of V naught is V naught squared is V naught. So this is V naught over root 2. Well, what is this quantity? This is something that's actually very, very useful. And it's what we will call the V, the root of the mean is like average, of the squared value. the root mean squared. So this is what we will call VRMS, which stands for the root of the mean of the square, the root mean squared value. So VRMS will be V naught over the square root of 2, the amplitude of our voltage over the square root of 2. And it will turn out that that is actually a very, very useful quantity. We'll see this more later on, but let me just mention, for an oscillating voltage, if we were to put just say like a resistor in here, we would likewise expect the current to have some oscillating form, like I naught sine omega t. Well, what would the power be for this circuit? Well, we know the power for any circuit we could write as IV. But what would the average power be? Well, the average power will go like sine squared, I naught V naught sine squared. If we look at the average power, it will turn out that it is just the I RMS value times the V RMS value. It turns out to be a very, very simple form. It looks just like the power that we had for the DC circuit, but now for an AC circuit, if we look at the average power, it's the same mathematical form, but all we have to do is use the RMS values as opposed to the constant values that we would have used for the DC circuit before. Now, we'll see this more later on. We'll talk more later about it, but I wanted to introduce it to you a little bit now because it's kind of right about the time that we're talking about current and voltage and things like that, so I just want to talk about what time-varying currents and voltages might look like. But we'll see that again later on. Okay, well that's all for now. Next time, we'll take a look at some more circuits and some more complicated applications of those circuits.